Three-phase motors part 2. The rotating magnetic field. All three-phase motors operate on a principle of a rotating magnetic field. There are three factors that cause a magnetic field to rotate. First, the fact that the voltages change polarity at regular intervals, and the fact that the voltages in a three-phase power system are 120 degrees out of phase with each other, and the arrangement of the motor windings around the inside of the motor. First, let's have a look at the three-phase alternator, the source of our three-phase power. With the three-phase alternator, we have three windings installed 120 degrees apart from each other. Now, when we put a magnet in the middle and rotate it, each of those coils is going to have a potential generated across them, and they're all going to be 120 electrical degrees out of phase from each other. This repeating sequence we can take advantage of with three-phase motors. Also, let's do a little bit of a review on the left-hand rule for coils. We're going to use that a little bit here. So with the left-hand rule, fingers go in the direction of the current flow, thumb points to the north pole of the magnetic field. Here's a diagram showing a two-pole stator. We have L1 wrapping around pole A1, and the other end of the coil is wrapping around over to pole A2. Now, if we can use our left-hand rule for coils and follow the current direction with it on this arrow here, we're going to loop our current around in this fashion. So that's going to make a north pole appear on this side, and the way the current's going to flow around the coil on A2, we're going to have a south pole on that side. So we're going to have the opposite poles across from each other, 180 degrees from each other on this stator. Here we have L2 connected to the coils wrapped around poles B1 and B2. Again, very similar configuration as poles A1 and A2, where we have the windings going one way around B1, loops around the back and over the front, and then the tail end comes all the way over and then connects and loops through. So B1, whenever it has a north pole, B2 will always have the opposite. And then lastly, we have line 3 here. It's going to follow a similar convention, except you notice it's wrapped a little differently here, more so for the sequencing of the north poles, which we'll look at in a few moments. But again, L3, it's going to wrap around C1 pole. The tail end of that line is going to connect up, and it's going to wrap in the opposite direction on the C2 pole. Now, you notice that all the lines from C2, A2, and B2 are tied together in a Y connection. These three-phase motors can be a delta or a Y connection, connected internally. Depends on the use they are for. So here, let's have a look at how the sine wave relates to the position of the magnetic poles. Right now we have A phase is peaking, and at that same moment in time we have B and C phase, our current is flowing in the opposite direction. So if we have, and we use our left-hand rule again, if we use our left-hand rule for coils, current's going to be wrapping around in this fashion and follow the arrows. We're going to have a north pole at the top, south pole at the bottom. Follow the line all the way through. Current's going to be traveling around and back up to the top here at that point of the sine wave cycle, and we're going to have a north on the top, and south would be down at this end. Now if we look at the other phases we have the current going in on this B1 pole here, where we're going to have the current is going to be wrapping around in this direction. And then it's going to produce a south pole on this side. In the opposite end of its winding on its B2 pole, the current's going to be going again in the similar direction, and it's going to produce a north pole at this time. And then the C is going to follow along. We're going to have the current coming in. It's going to create a south at this side of the pole. All the way through, we're going to have a north on the opposite side at this point in the sine wave. So if we carry on to the next increment in time, where now we have A phase is a little further down in the cycle. We have C phase crossing. It's going to be at 0. So there's no current flow in that moment in time. And then B phase is going to have the equal and opposite amount of current as A phase will. So at that moment in time, we're going to have equal strength poles on B2 and A2 north, and equal south poles strengths on A1 and B1. And C has no current flowing through it, so it's north and south. There is no north and south poles on C. And then carry on through to the next step, where B phase is peaking in the negative, and we have A and C crossing. So now we have B phase is going to be at the negative half cycle, which is going to produce the current going into the winding, and then it's going to be curling around, creating a south pole on this side, and then it's going to make the corresponding north pole across from it. And then our phases A and C, they're going to have a weaker pole, and because they have a less current going through each phase. Okay. And then in the next increment in time, we have A phase crossing 0, so it's going to have no north or south, and the poles have shifted. And then the next increment in time, we have C phase is peaking in the positive, then we have a negative B and A phase. So we are peaking phase now is going to have the stronger pole strengths compared to the other two. The other two are going to have a weaker pole strength. So if you notice, and I'll go back and replay it, you can see the shifting of that north pole is starting to do a rotation. The next increment, it shifts again. Now we have B phase is de-energized with no current flow, so we have no north or south poles there. And then the next increment, again, we have A phase is peaking in the negative half cycle, so its polarity, where it originally started the cycle, where this was south and this was north, now it's flipped because we have at the negative half cycle. And then later on, at the next one, where A is going to cross the 0 again, we have the equal and opposite currents at B and A phase. Okay, so then we're going to have a south pole on B2 and a south pole on C1, and a north pole on B1 and a north pole on C2. So again, it's shifted. So and then finally we are back to where we began, where we started off with the current flowing out of line 1, creating a south pole on the A1 pole and a north pole on the A2. So if I go to the next slide, what happens is, so here we have a animation in real time showing as the three-phase sine waves cycle, positive and negative, 120 degrees out of phase, that causes this north and south pole to rotate around in a circular fashion around the perimeter of the stator. Here we have an energized three-phase stator and a compass. Watch as I enter the compass into the magnetic field. the compass starts to spin. The north pole pointing part of the compass is trying to follow the north pole of the rotating synchronous stator field. It goes faster as we get closer to the stator core because the flux lines are more dense at that point. Now, what would we do to change the direction of that? It's just a simple fact as reconnecting our line 1 and our line 2 to the different sets of poles. So shown here in the previous slide, we had L2 going to B1. Now we connected it L3 to B1 and L2 to C1. What that does is it's going to make the cycle of the sine wave, instead of going in ABC, now it can go CBA. As shown, we've changed the direction. As we just saw, by changing 2 stator leads, we can reverse the rotation of a 3-phase motor. It's also good practice to identify the correct rotation of these 3-phase motors before we connect them to a mechanical load. To determine which direction the motor will be rotating at, we have 2 basic ways. One is to make the electrical connection to the motor before it's connected to its mechanical load and do a thing called a bump test, which is a small energization just to see what way the motor is going to turn and de-energize. The other is use a phase rotation meter to compare the phase rotation of 2 different 3-phase connections. Let's look at synchronous speed for a motor. Synchronous speed is the rotational speed of that magnetic field in the stator of these 3-phase motors. It is determined by the number of stator poles per phase and the frequency of the applied voltage. Here we see 3 different types of stators. We have a 2-pole 3-phase, a 4-pole 3-phase, and a 6-pole 3-phase. Frequency of the supply voltage will determine the speed of the rotating magnetic field in your stator. We use variable frequency drives often to control the speed of these motors by altering their frequency. So if we change the frequency, if we decrease from a 60 hertz sine wave to a 50 hertz, we're going to have less cycles in the same time. So what effect it'll have on our rotating magnetic field here is we're going to have slower transition times from south to north and north to south. So as we decrease our frequency applied to our stator, our rotating magnetic field will slow down. And then also the opposite happens. If we increase past 60 hertz and increase the frequency, it'll speed up the rotation of the magnetic field. So to calculate the synchronous speed of a motor, we need to know the frequency and the number of poles of the motor. Now, all 3-phase motors are going to have either 2, 4, 6, 8, or 10 poles. So to calculate the synchronous speed, we get 120, which is a conversion factor we use, multiplied by the applied frequency and divided by the number of poles. So knowing that, let's calculate what the synchronous speed will be for a 6-pole 60 hertz 3-phase skim. We use our formula, speed equals 120 times frequency divided by poles. So we have 120 times 60 hertz divided by 6 poles. And that'll give us 1200 RPM. Now, what would happen if the motor is running at a slower speed because it's being operated at a variable frequency drive, let's say? Can we calculate what the frequency is? Yes, we can. We can use the same formula where we'd populate the values in like so. We know the speed, 400. We know we have 6 poles, but we don't know our frequency. So if we transpose our formula, we have 400 times 6, 400 RPM times our 6 poles divided by our constant of 120. And that's going to give us 20 hertz. This chart shows 4 different types of stator pole configurations and operating at 2 different frequency settings and their corresponding synchronous speeds. So let's look at the squirrel cage induction motor. The squirrel cage induction motor receives its names from the type of rotor, the rotating member used in the construction of the motor. If the metal laminates were removed on a rotor, you would see something like this. You would have 2 end caps with bars skewing across it. Those are the conductors on the squirrel cage rotor. And this is how it gets its name squirrel cage, because it kind of looks like a hamster wheel or a squirrel wheel. Here we have a cross-sectional cutaway of a squirrel cage rotor. The laminates are the solid parts here. Here's the motor shaft. And then here you have the rotor bars. Okay, the rotor bars again are the conductors that are going to carry current from one end of the rotor to the other. So the principles of operation of the squirrel cage induction motors: we need 2 magnetic fields necessary for it to rotate. We have the stator magnetic field and the rotor magnetic field. Before we get any further, we have to have a little bit of a review and an introduction for some of you of operating principles for conductors in a magnetic field. So if we have a conductor in a magnetic field and we put a current through it, as we see here, the X means the current's going away from us. That means if you use your left-hand rule for conductors, we're going to have a rotating magnetic field around our conductor in a counterclockwise direction from our perspective right now. If we have a north and a south pole in this configuration and we have the current going into that direction, where the lines are going in the same direction, they're going to try to repel each other, which is going to force that conductor up. Okay, that's called motor action. So we can see that again if we have 2 conductors. Let's say they were looped together. We have the north and our south pole here. We run current through these conductors. The current's going away from us, so the current's going to go in a counterclockwise direction here. Current's coming towards us, it's going to go in a clockwise direction. So remember, when the lines are going in the same direction, as in this side of the conductor, are matching with this, these, similar to the rule of like poles repel and unlike poles attract, same concept happens here, where the conductor is going to get pushed up through in the upwards direction, and this conductor is going to get pushed down. And if we had these coils connected to a shaft, it would cause a rotation. The right-hand motor rule provides a simple way to determine the direction of force acting on a conductor. We use our first finger or index finger for the direction of the field, our middle finger for the direction of the electron flow, and our thumb is going to show us the direction of the conductor. So here we have on the right-hand rule for motors, and on the left we have a left-hand rule for generators. So let's have a look at the left-hand rule for generators. Very similar to the right-hand rule for motors, where the thumb is going to be the motion of the conductors, the index finger is going to be the direction of the magnetic field, and your middle finger will be the direction of the electron flow. So if we look at this generator here, if it's rotating in a clockwise direction, and our north pole is on our left, our south pole is on our right, our magnetic lines directions are going to be going from north to south across in this direction. And if we're rotating in a clockwise direction, we use our index finger to point in the direction of the magnetic fields. We use our thumb to point in the direction in which the conductors are moving. So at this point here, our middle finger is going to be pointing away from us and is in the same direction in which this X is signifying that the current is going away from us. Now if we go over to the other side for the DC motor here, we are actually putting current into these conductors. We have the magnetic field already in place, so we have to use our right-hand rule now. So if we put our index finger pointing from north to south, and if we have current going away from us, that's going to make our conductor get forced in the upwards direction. And then likewise for this one, we have the current coming towards us and the magnetic field's going in the same direction. Our thumb is going to be pointing at this side downwards to indicate that the current conductors are going to be going in the downwards direction. We need to know these rules for the next step on understanding how our three-phase squirrel cage rotor works. Now let's get into the stator-rotor interaction. So what we have here is magnetic poles. These are representing the rotating field of the stator. This rotating field is going in a clockwise rotation. Okay. Now here we have this representation is of the rotor bars. Here we got the end plates on the rotor, and we got the rotor bars that are going the length of the rotor. This is the main electrical circuit in the rotor. We have the north poles here with the lines coming out. We have south poles here with the lines going in. Okay. Now remember this magnetic field is rotating in a clockwise direction. Now, for this rotor to develop a magnetic field, it needs some current flowing through it. These arrows represent the current flow directions, but let's have a look and prove how that works. We're going to use our left-hand rule for generators and our right-hand rule for motors to explain how the rotor rotates. Okay, so using our left-hand rule for generators, we're going to point our index finger in the direction of the lines of flux, which is going to be downwards. And now we have to have a look at this. When we're looking at the left-hand rule for generators, we're looking at that left-hand rule in the perspective of the conductor that's moving through the lines of flux. At this moment, the conductor is staying still. The lines of flux are moving. So if the lines of fluxes are moving in a clockwise direction, it's the same as the conductors moving in a counterclockwise direction. So if our index finger is pointing down, our thumb has to be pointing upwards and then over to the left, which means our middle finger here is going to show our current direction is going to be going in that direction. Okay? Hopefully that made sense. Now we've established that the current will be going in this direction when our rotating stator field is going in a clockwise direction here. Okay, so now we have our current's going to be going around and back. We can do the same left-hand rule to establish what current direction is going to be through this rotor bar also, but our lines are going to be going upwards instead. So just a matter of pointing the flux up, and the thumb's still going to be going over in the same direction, but our current now is going to be coming towards us if you use your left-hand rule. Now let's see which direction our rotor is going to be moving. If we use a right-hand rule for motors, okay, our index finger is going to be pointing in the direction of flux, so it's going to point down from our north pole down, okay? And our middle finger is going to be pointing in the direction of current flow. So that's going to be pointing away from us across here. So our index finger is pointing down, our other finger has to go away from us. Our thumb is going to be pointing downwards. So it's telling us that the rotor is going to be rotating in a clockwise direction, as shown by these arrows here. Okay, a little complex. You know, you might have to replay this section a few times to kind of visualize what's going on. Here we have an animated slide of a rotating stator field. The speed at which this is rotating is dependent on the number of stator poles and the frequency of the applied voltage. When we have a squirrel cage rotor placed in the stator field, the rotating magnetic field will cut through the bars shown here. This is one type of a rotor bar. There's a couple different designs we're going to get into later. This cutting action will induce a voltage, such as this. And as soon as we have a voltage induced in the rotor bars, current is going to start to flow. Current flows in these rotor bars. They develop a magnetic field. Those magnetic fields interact. The stator magnetic field and the rotor magnetic fields start to interact, and the rotor starts to rotate. Rotor slip. The rotor of an induction motor can never turn at synchronous speed. If the rotor were to turn at the same speed of the rotating magnetic field, there would be no cutting action. And there would be no potential induced in the rotor bars, and there would be no current flow. Now, the difference between the synchronous speed and the rotor speed is called slip. Slip is measured typically as a percentage. And this is how we calculate it. So if we had a synchronous speed of a motor at 1800 RPM, the motor has a full load speed of 1740, what would the slip be? Well, we use this formula here. For a percentage, right, we get our synchronous speed, we subtract our rotor speed, so 1800 RPM subtract 1740 RPM is going to give us 60 RPM, divide that by the 1800 is going to give us 0.033 or 3.3% slip. Okay, that's our percent slip. The slip speed is the 60 RPM. The slip speed is the difference between synchronous speed and rotor speed. When motors operate at no load, the rotor will turn close to synchronous speed. This is because when there's no load on the motor, all it needs to overcome is windage losses and bearing friction. So very, very, very low amount of load on it. So you can see an 1800 RPM motor running close to 1796 RPM, very close to synchronous speed. So when load is added to the motor, it cannot supply the torque necessary to turn the load at its present speed, causing the rotor to slow. When the rotor slows down, the cutting action between the rotor and the magnetic field and the rotor bars increases. Okay, so when we're at full speed, no load, our rotor is rotating near synchronous speed. As we add some load to it, that's going to slow the rotor down. When the rotor slows down, the cutting action of the stator lines of flux going through the rotor bars is going to increase. What happens next is, well, the relative velocity, we have We have EG equals BLV here, if you remember from last year. B meaning the flux density, L is the length of the conductors, and V is the velocity. Well, the generated voltage now in our rotor bars is going up because the relative velocity is increased. Okay. Now, the generated voltage is increased across our rotor bars. That means the current going through the rotor bars will go up. Okay, and when we have current increase in a conductor, the magnetic field around the conductor increases. Okay, so if we look quickly at this torque formula, which we're going to get into a little later on, just understand this formula here. We're not going to use it for calculations. This formula is purely as an explanation to explain what's going on here. We have our torque on our motor shaft here. Okay, it's equal to a constant here, which is construction constants for the motor, and multiplied by the flux strength of our stator, multiplied by our current in our rotor, and then the power factor of the rotor. We'll look at the power factor of the rotor a little later on, but if our stator flux stays the same and our rotor slows down a little bit, our rotor current will increase because the induced voltage is going up, which is going to increase our torque, which is going to compensate for that increase in load on our rotor. Okay. Now, that difference in speed from full load to no load is what we call speed regulation. Okay, is the difference in speed between the motor at no load to the motor at full load. Okay, so a typical 1800 synchronous speed motor, let's say, is running at full load speed of 1725 RPM. At no load, let's say that motor speeds up to 1797, which is close to synchronous speed. Well, if we add load to the motor to get it maximum full load to the motor, and it slows down to its 1725, what's the speed regulation? Well, to find that out, the speed regulation, we got the no load speed, which was 1797, subtracted by the full load speed, 1725. It's going to give us a 72 RPM speed regulation here. Also, we can get that as a percentage by dividing that speed regulation RPM by the full load speed, then multiplied by 100. So again, we'll say 1797, subtract 1725, then divide it by 1725 again, multiply by 100, will give us 4.17% speed regulation for this particular motor. Okay. Rotor frequency. Rotor frequency is dependent on the amount of slip there is in the motor. If the rotor is not rotating and the stator is energized, the rotor frequency will be the same as the supply frequency. As the rotor accelerates to full speed, the frequency of the rotor decreases. Shown here is a transpose formula that we use for calculating synchronous speed. We're using it here to calculate the frequency of our rotor. So we have our number of stator poles for this 4-pole motor, the frequency we're going to calculate, and the slip RPM. Now the slip RPM is the difference between the rotating stator synchronous speed and the rotor speed. Okay, so the rotor stationary, the 4-pole motor synchronous speed is 1800 RPM. So the difference is 1800 RPM. Okay, so we go 4 times 1800 divided by 120 is going to give us 60 hertz. Since the rotor is not rotating and the stator is energized, the slip speed equals the synchronous speed. 1800 RPM sync and 1800 RPM slip. But when the rotor is at full rated speed, the rotor frequency drops to a very low amount. When rotating at 1750 RPM, the slip speed is 50 RPM. Therefore, the rotor frequency reduces to 1.66 Hertz. Shown on the left here is 0 RPM rotor speed. So our slip speed is going to be 1800 RPM for a 4-pole motor. And then here we have our little equation calculating what the new frequency would be like with our slip speed of 50 RPM. Now the starting currents for the squirrel cage motors can get quite high. They'll draw the greatest amount of current when started. This is called the starting current, the inrush current, and also called the lock rotor current. At the moment a motor is started, the rotor is not turning. Okay, the rotating magnetic field will cut the rotor bars at maximum rate, causing the maximum induced voltage. Since the rotor bars are shorted together, the rotor's current will be a maximum also. This maximum rotor current causes the stator to draw maximum current as well, causing a significantly high inrush current.